In this lecture, we're going to talk about eliminations or elimination reactions and some of the nuances in elimination chemistry. And there are, like SN1, SN2, there are elimination reactions called E1 and E2. And what I've started drawing here is a potential pathway of either elimination or substitution in a unimolecular sense. And I've got what I've basically just called A minus. So that's an anion. And this we don't know anything about. It can either be a pretty great nucleophile or it could be a pretty great base. And in either case, in an E1 or an SN1 pathway, the first step is dissociation to the formation of a carbocation. And in that case, what we see is we form a carbocation on a secondary center, and then one of three things presumably can happen. The first one I've illustrated is that you have a hydride shift. You have potentially hydrides here, and you may be tempted to think that maybe you can put a positive charge out on this double bond for some reason. And I want to assure you that vinyl cations, that is to say, don't put a positive charge on a double bond ever. That is less stable than methane with a positive charge. And the reason is because, as we discussed in a long lecture ago, these are actually electronegative. So these are not withdrawing. sp2 carbons are electron withdrawing. So you've got a pretty electron, or you've got an electron withdrawing carbon over here next to a positive charge. So they're pretty destabilized. So in that sense, you don't want to put a positive charge on a double bond. So that's not really a pathway open to us. And in the sense of rearrangement, it doesn't really make a whole lot of sense because it doesn't actually move the carbocation to a more substituted carbon anyway. But this way also works, where you could have a hydride shift. So in this case, the hydride that was right here, that hydride actually just went right here, and it put the carbocation on this carbon. And now you have that carbocation, or we have this. All right. Most likely in this particular instance, you may want to look for a rearrangement to try to get this positive charge. But what I would say is, in this particular case, I don't think you're going to see a rearrangement at all. Right? So I'm going to actually dot that line and say no. And the reason why I don't think you'll see a rearrangement here is because this cation is actually now conjugated. All right. So you have a conjugated system, and if you do that hydride shift, you break conjugation. So, and this is a good example of, your rearrangement may give you a more substituted atom, but at the expense of conjugation. And conjugation is a more stabilizing force than just putting the carbocation on a tertiary center than on a secondary center. So I'd say that probably our reaction is going to go from that substrate, which means that in an SN1 type reaction, our final product would be, just a substitution of that iodine with the nucleophile in that particular case. Now, if it's an E1 elimination, so if that's an E1 reaction, what would happen is, instead of being a nucleophile, it would be a base. And if you have a positive charge right here, that means that the proton here is going to be much, much more acidic. It is going to be, those electrons are going to be pretty primed and ready to be dumped right into that positive charge, okay? And so that product would then actually make a more stable or a lower energy double bond. Okay, so this would be your elimination product, and this would be your substitution product. Okay, and an important point of E1 versus SN1 is that if you look at the energy diagrams of both of these reactions, they will have been the same. So in the sense of a E1 reaction or an SN1 reaction, we always have this initial rate limiting step, and then we have some smaller component here. And the non-rate limiting step doesn't influence the rate of the reaction. Okay, an SN1, if you're given a substrate, if you're given a alkyl halide, an SN1 or an E1 reaction, the same concentrations of your substrate. So if I gave you this compound right here, what I am saying is that the formation of this product and this product will happen at the same rate if it's an E1 or an SN1 reaction, because the only rate that mattered was the formation of this carbocation. The next step, either the deprotonation to give you elimination or the substitution, that didn't factor into the actual speed at which the reaction occurred, because in all those cases the only actual thing that mattered for the rate was the formation of this carbocation. Now, what influenced the next step, all right, what influenced that? The influence there is primarily about what substrate you use, all right? So if we had defined A minus, all right, if we had defined that in the first place as something that looked like a base, okay, so something that was a hard base that was more along the lines of anions with negative charges. So things like O minus, ethoxy, amides, all right, these sorts of things, hydroxy, those tend to push towards elimination reactions. Things that tend to push towards a substitution reaction, so are the bigger sort of sulfur, that tends to push you towards, because sulfur, remember, that's a good nucleophile. So, and then things that are even bigger than sulfur, of course, are excellent as well. Selenium compounds. And then things that are not protonated, or I'm sorry, things that are protonated, like ethanol, water. These things are pretty good nucleophiles in both SN1 and E1 reactions, okay? But up here, these are better bases. And these lead to E1 reactions, all right? Whereas down here, these are better nucleophiles, and they lead to SN1 reactions. I should write that. They lead to SN1, all right? Now let's try a different scenario, all right? Where you can have, where there's less ambiguity on the potential outcomes of where that carbocation is going to go. So that carbocation is pretty much not going to move at all. And in this particular case, it's not going to move at all either. But the location of where the base comes and grabs protons, all right, where it comes and deprotonates is important. All right, so if we have, say, this molecule, right, and we're going to do an E1, so this is an E1 reaction, so this is an elimination. That means that our first step is going to be the formation of a carbocation, and that's going to form this planar looking thing here, and you've got a lobe and a lobe, all right, and the next step is to decide, all right, what proton is going to be pulled off in order for us to make this double bond, right? So if it's an elimination, we're going to make a double bond. And we can see that we have a couple of protons, right? We can either come in and we can deprotonate this proton back here, okay? And that would lead to, which is also this proton here. And if we deprotonate there, that would form a double bond between that carbon and that carbon. And so we would end up with something that looks like that. Or we could deprotonate one of these carbons, all right? And if that came off, then we would have a double bond that goes down there, and we would end up with something that looks like that. Okay, so which one is it? The rule of thumb here, actually it's not just a rule of thumb, it's actually called Zaitsev's rule. All right, so Zaitsev's rule, or I guess the Zaitsev rule, I don't think it's got a possessive. The formation of the more substituted product is thought to be observed more frequently because more substituted double bonds are more stable. This product would form probably as a minor product. So it's probably good to point out that organic chemistry is not black and white. You'll probably see more of this product than this product, but that's not to say that this product can't form. It just is a minor product. And what we would call these two products are the Zaitsev product, and this one's called the Hofmann product. The Hofmann product is the less stable terminal. All right, so this is a terminal, as in it doesn't have any substitution on it, alkene. All right. Now, E2 eliminations, on the other hand, are the synthetic equivalent of SN2 reactions. And an E2 elimination has the same sort of bimolecular rate diagram that an SN2 reaction. So that means that you have one transition state and then finally a product. So in this case, both the base, whatever that is, and the substrate are going to have to be in this final transition state. And that final transition state is just going to have to look like something is forming a double bond. So if we have to sort of conjugate whatever that is, let's make this substrate a little bit real so that we can figure out what it is that we're going to make. All right, so there's a BR, and then we'll just say there's some, that's it. We'll just say it's that, all right? And so there are two methyl groups here. These are methyl groups, and then that's a CH3. So what would that look like? All right, well, we're going to form a double bond. So in the transition state, that's obviously got to be forming. Can't be have formed, otherwise that would probably be the product. And two things must be happening. One, this bromine must be coming off, so that must be getting pretty far away. And this proton over here, let's give it a slightly different color. Let's go ahead and just color the protons. Now all these protons are of course the same in principle until one starts getting pulled off. And we'll just say that that proton that's getting pulled off. All right, so that proton's coming off. And then there are these two other hydrogens over here that are just participating, and then there's these two methyl groups over here. And so that's the transition state of a E2 elimination. You've got the base starting to pull off that hydrogen, that proton there, and that is going to result in the collapse of the electrons that hold the hydrogen to the carbon. Those are going to go down here to make the double bond. And then the electrons that used to form this bond, this carbon-bromine bond, those are going to just go plop right onto bromine. And then you end up with your final product. All right? So an E2 elimination happens all at the same time, just like an SN2 elimination. And it has In order for this all to work, it has to have a pretty strong base. Something that is, we'll say, we'll even use these bases back up here. Ethoxide, for instance, that's a fairly strong base, and it is pretty good nucleophile. Now, the reason that you don't see nucleophilicity in this particular instance is because this bromine is on a tertiary carbon, and SN2 reactions don't occur on tertiary carbons, so you're pretty safe to use a pretty strong base that's also a pretty good nucleophile. And in order for this reaction to work at all, you do really have to use a pretty strong base. It would also be helpful, if you really want to discourage a nucleophilic attack, to use a really big base. And there are a couple of really big bases. So really big and strong bases, like, let me switch back to my white marker, like something that's a nitrogen, by the way. And then usually this nitrogen has a lithium salts. And so this is a really strong base, and this is really truly only a base. You don't really see this because of these big isopropyl groups coming off of it. This base is called lithium diisopropyl amine. Lithium diisopropyl amide. That is a wicked strong base, and it's not a good nucleophile because, as I said, these groups are huge. They're not going to allow it to be a nucleophile. So you see that kind of base, essentially you are guaranteed an S or an E2 type elimination. All right. There are other bases that are also pretty well known. So ethoxy, that's a strong base, but you saw it up there in the E2. It can kind of go both ways. What if you wanted to use an ethoxy that you were guaranteed a good E2 reaction? You can use T-butyl alcohols, okay? So this is usually sold with as the potassium salt. So that's potassium O T-butoxide is what we would call that, potassium O T-butoxide. That's also a really strong base because it's got all of these CH3 groups. Those are all inductively supercharging this oxygen here. And then there are some other bases that are not charged. They don't have any charge associated with them at all. They have lone pairs. But they are also really, really powerful bases. Nitrogens, of course, as you know, have lone pairs. And you can draw a bunch of synthetic nonsense all over, a bunch of stuff that, really makes it bulky and makes it really quite big. So that nitrogen there cannot get in to do any sort of nucleophilic reactions, but it can come in and deprotonate. And so if you see an amine here, a nitrogen, say with its lone pairs, those are great bases, all right? And if it's really bulked up like that, and this particular one is called DBN, all right? And that is a long name, 1,5-diazobicyclo-4,3,0 nonane. We just call it DBN for short. That's also going to be pretty good at doing E2 eliminations because it is a base. Nitrogen with lone pair, we call them nucleophiles all the time, but like, look at this thing. It's huge. It's not going to be a nucleophile. It only has one real outcome, and that is as a base, all right? Now, when you have a base like this, and you're doing an E2 elimination, we really have to look at how this elimination just happened. I mean, look at this look at this transition state, all right? It's a fairly complicated looking transition state. And in order for an E2 reaction to occur, it has to be in the transition state, has to be in a very specific conformation, right? So if we look at how this happens, let's resume. Let's go back to this molecule and just illustrate E2 eliminations. All right, I'm going to draw it down here. All right. So I'm going to even incorporate some of the stereochemistry here so that it's very clear that these have to be in pretty much an orientation that looks like this. All right, so let me just move this down a tad. And it has to look like this because our final product, if we draw it out, is going to look like this. Okay, it's going to have a carbon, it's going to have a hydrogen coming over here, it's going to have a hydrogen pointing out towards you, it's going to have a double bond. That's going to be also a pi bond there, so we're going to have a pi there, and it's going to look like that. All right. Now the transition state, in order for us to get to this point, is going to have to favor, and I'm going to highlight these, it's going to have to favor the formation of that double bond here. And how do we favor the formation of a double bond in this particular case? All right. So we have to remember that the transition state is going to be some sort of amalgamation of starting material and product. So if we look at what we're forming in the transition state, and we just sort of draw it out sort of as like a hemi intermediate. Well, just it's not an intermediate, it's a transition state. But if we kind of draw it out like, you know, how are we going to form a pi bond here? And with something that comes out here. Essentially what we're going to do is we're going to try to, at the same time, pull all these things off and make the pi bond, all right? And you know that if we look up here, the pi orbitals have an orbital above and an orbital below, and there's really no distinction. I can draw, there's pi, there's electron interaction on both sides of those. I try not to draw it that way because it looks like a triple bond, but you remember the triple bond actually has another p orbital that pops out. But there's electron density below and above the double bond, all right? And that's got to form, which means that if you're going to form your pi orbitals, you're going to start looking at, okay, so this is going to be one of those lobes, and this is going to be one of those lobes. So in order for these to be forming at the same time, the proton that you're going to be pulling off has to be 180 degrees away from the leaving group. And because if you have a base coming in, and it's just going to pull that off, it's going to be like the flickering of an incandescent light. It's going to go bzz, 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 and then that bromine's coming off, all right? All at the same time. So this has some pretty specific geometry requirements, all right? And that you are, in order for this to happen, your proton has to be locked into the configuration that is anti to your leaving group. All right, so if we want to start drawing, in fact, we probably should start drawing some Newman projections to see how this can actually influence the outcome of a reaction. All right, so let's say we have a reaction like this, and you have a proton here, and then we're going to do an elimination in our bromines here. So we've got those in 180 degrees, so that's good. All right, and here are our substituents. CH3, and then we got a pH over here. That's an aromatic ring. That's a big phenyl group. All right, call that pH phenyl. Remember, pH phenyl is equal to basically looking like that. All right, and then that attaches to, you know, the carbon there. And then we've got a proton coming off here. All right, what we see in this particular case, because look at our structure, the phenyl group, that phenyl group is pointing away from you, and that phenyl group is pointing towards you. This is the only direction that this elimination can occur. And that means the only product that can occur is this trans configuration where the phenyl is up here and the other one is down there. All right. So let's look at this using the old eyeball of science right down here. All right. If we look at it down there, what we see is we have the bromine coming down, and the hydrogen is going to point up, and then we've got a pH group, a phenyl group coming off over here. Behind that molecule, what we see is a phenyl group actually now going in the opposite direction here. And the CH3 group over here. And then the proton coming up over here. All right. And so this is our little eyeball of science. And this shows the geometric requirements of your chemistry. All right. And you can even draw the transition state here, because if we throw in our base, the base is right here, and the base is going to come in and snatch that proton, and you're going to start forming the double bond right here as that thing pops off. And that is going to lead to that product. All right. So let's right quick talk about six-membered rings. We've just briefly reviewed some six-membered ring business, right? We talked about it a while ago, but it's worth rehashing it out. So in a six-membered ring, if I drew you a six-membered ring and drew this up and drew this up, all right, so that those are cis to each other, that would look like a chair, so that would be equivalent to a chair. That was drawn this way, where one of those CH3s was pointed up and axial, and one of those CH3s was pointed up and equatorial. Now, there's a flippity-flop process, a chair flip, that will allow us to actually change these in a way that the chair that was axial is still up, but it's now up equatorial, and now this one is up. The drawing there isn't the best in the world, is up axial. Likewise, we can draw a chair conformation, and instead these can be trans to each other. All right. And if we draw our chair conformations, what we see is in the trans configuration, the preferred position is going to strongly be them both be in the equatorial position, because remember A13 strain, where this one is now down. Of course, what's axial is the proton, right? And this one is up. What's axial here is the proton. The flip, the chair flip, in this case is disfavored. So you've got a little arrow that points that way and a big arrow that points that way. Because remember, up here, no matter what you do, you always end up with something that's axial. Here, you have the benefit of making sure nothing is axial, so you never have any sort of this A13 strain, which again, if I remind you, is the interaction with this hydrogen being axial and this hydrogen being axial, and then these protons bonking into those things over there, right? A chair flip is going to be less favorable in this case, because now we're going to end up with something that is, again, going to be axial, and this is going to be axial. They're both trans still, but they're now both axial, and that's less favorable. Now, in order for an elimination to occur, eliminations must occur axial and anti. Axial and anti, all right? So in order for you to do an elimination, everything has to be axial, all right? So if we just draw a six-membered ring, call it that, all right? And that, of course, doesn't look like a flat hexagon. It looks like something that looks like this. It's not beautiful, but all right. And then the chlorine is going to preferentially be in the axial position, though there's there's little consequence for the chair flip here because the A13 interaction with the chloride isn't huge. Because it doesn't have like stuff coming off, like methane has protons coming off of it that can bump into stuff, but it can still flip, and that'll give you a chlorine up here. Now you can see that you can do an elimination reaction here, right? Because you have to have this chlorine 180 degrees from the hydrogen you're going to pull off in order for that reaction to work. In this particular configuration right here, your chlorine and the proton are not 180 degrees, right? So if we look at our eyeball of science down here, what we see is that you have a hydrogen here and a hydrogen here, and then the rest of the ring system down there. And over in the back, you have a chlorine down here and a hydrogen here, and then the rest of the ring system up here. All right, and you can't have an elimination that's not 180 degrees as an E2. This is all strictly E2. You can still do E1 eliminations and they not be anti. That has nothing to do with E1 eliminations. I'm saying for E2 eliminations, they have to be overlapping. And so what we have here then is a necessity that this flip. Not a big barrier to that, but they have to flip. And so you end up with this, and we'll draw our eyeball down there. And if we draw our eyeball down there, what we see is the appropriate proton, the one that's going to have to be deprotonated, is now pointing down. And then you have your hydrogen over there, and then this goes off to the rest of the ring. And then in the back, you now have your Cl in the back. All right, and then the, I didn't draw it, but there's the hydrogen coming down there. All right, and then the rest of the ring is coming off, and that's going to go off and form your 6-membered ring. And I've kind of shortcut it here. And now once it's in that configuration, you can have your base come in. All right, and then I can grab that. And then the pi, then you can flicker it like the bzz, 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 and that comes on here, and then the chloride leaves. All right. In that case, if you have these really, if you have that overlap and you've satisfied the, we'll call that strict geometry requirements, REX. If you satisfied those for the E2 condition, then you can have an E2 elimination. All right. And that is essentially the important part of that. Then there's a sort of interesting example of an elimination where you can't, under any circumstance, it's still a 6-membered ring, right? And these bicyclic systems are something you've always got to be looking out for. And you can have a chloride here, and what you'll never see is the formation of a double bond here, all right? That reaction doesn't work. Actually, not just because you never really get the alignment. So if you look at the geometry of these systems here, oops, and you draw out the hydrogens here, you can see that this is going to come out sort of at you, and then these are sort of locked into place. There's no flipping back and forth. The reason actually, beyond just E2, you can't actually make the chloride and the hydrogens overlap appropriately. You can't even do an E1 elimination on to form a double bond at the bridgehead position of a bicyclic system. This is actually called Brett's rule. All right, and Brett's rule essentially says that you just can't form any sort of double bond at a bridgehead position because the geometry of this double bond that you get here, this weird looking thing where that's going away from you, and this just doesn't work. So in the Norborning looking things, those sorts of systems, they don't actually work very well. That's not to say that all bridge systems are going to be problematic. You can actually have good elimination with other bridgehead systems. In particular, you can have good elimination in Decalin. So Decalin also looks like this. This is a system that is a bridge system. All right. And what Decalin has is you can have two different isomers. All right. One is trans Decalin. Say, for instance, you have a chlorine there, and a cis Decalin, where you have a configuration that looks like that. All right. And these actually are totally different shapes, totally different ring structures. What you have in transdecalin is actually a pretty comfortable looking ring structure, and the axial positions here just sort of fill themselves out. Cisdecalin, on the other hand, that's a kind of a different looking thing altogether. In a cisdecalin system, you still have this ring position, but it's no longer as convenient. So one hydrogen, we'll say that's still axial, and then the chloride is going to be equatorial. And so when you draw out the other ring as it comes down, what that starts to look like is something that looks like that. So you have a ring position that looks more like that. And so there's no way to interconvert these two structures, cis and transdecalin. Those are essentially locked into place. And so you can see that the cisdecalin, the transdecalin, sorry, this one is geometrically predisposed to actually undergoing an E2 type elimination, whereas this cannot. So bicyclic systems can offer some surprises, and you have to think about the three-dimensional structure in order to figure that out.